July 18, 1945, 2:23 p.m., Lockheed Headquarters, Burbank, California. Chief Engineer Clarence Kelly Johnson stared in disbelief at the German engineering drawings spread before him. The Messerschmitt Me 262 turbine blades survived temperatures of 680 degrees Celsius thanks to a system of microscopic air channels. Each blade contained 127 cooling holes, precisely 0.4 millimeters in diameter. The American Whittle turbines were failing at just 540 degrees. Johnson grabbed the phone and called Colonel Donald Putt at Wright-Patterson Air Force Base. His voice trembled. "We're 10 years behind, maybe 15. These German engineers have reinvented physics." The file in front of Johnson was stamped "Classified, Operation Lusty." On March 28, 1945, Captain Robert Kempel had seized 14 intact Me 262s in Oberammergau, along with 342 filing cabinets filled with technical documentation, 127 tons of paper. Construction plans, test reports, material specifications, all documented with meticulous German precision. Johnson had spent 3 weeks studying the drawings. Now he understood. America didn't have a jet engine. America had a working prototype with a fatal weakness. The Germans had created a production system that was defying the laws of nature. The numbers were shocking. Me 262 turbines ran for 25 hours between maintenance. American jets managed just 7 hours. German engines produced 900 kilograms of thrust with a weight of 720 kilograms, a ratio of 1.25 to 1. The best American designs reached only 0.87 to 1. But the real genius lay in the turbine blades. Johnson had brought in metallurgists from MIT, professors from Caltech. No one could explain how the Germans had done it: hollow blades with internal cooling channels, airflow through microscopic holes. Precision that American machine tools simply couldn't achieve. The technical report lay open to page 127. Technical Intelligence Report, number 432. Authored by Colonel Harold Watson, July 14, 1945. Watson had personally inspected the Messerschmitt plant in Augsburg. His words were damning. German turbine cooling calls into question everything we thought we knew about high-temperature aerodynamics. Their boundary layer control is 20 years ahead of our research. Without this technology, America will never build competitive jet aircraft. Johnson knew that Watson was right. Lockheed was working on the P-80 Shooting Star, the first American production jet. But the General Electric J-33 engine was a disappointment. Too weak, too hot, too unreliable. The turbine blades were melting after just 40 flight hours. General Electric had invested 18 months and $42 million. Without a breakthrough, now the German solutions lay before them, stolen, seized, justified as war booty. But Johnson was engineer enough to recognize the truth. This was the most valuable technological transfer in history. The Messerschmitt drawings showed every detail: blade number T47B, length 82 millimeters, width 12 millimeters at the base, thickness 3.2 millimeters, hollow inside, wall thickness 0.6 millimeters, 127 cooling holes arranged in a spiral, each hole precisely 0.42 millimeters in diameter, tolerance plus or minus 0.02 millimeters. The holes weren't randomly placed. They followed precise aerodynamic calculations. Cooling air was diverted from the compressor, 3.7% of the total airflow. This air flowed through the hollow blades, exited through the microscopic holes, forming a protective film on the blade surface. Boundary layer cooling. The concept was brilliant, the execution superhuman. Johnson had consulted with drill manufacturers. In 1945, no American machine could drill 0.4 millimeter holes in hardened steel with 0.02 millimeter tolerance, over 127 holes per blade, with 76 blades per turbine. That meant 9,652 precision holes per engine. The Germans had produced 5,000 Jumo 004 engines. That was 48,260,000 precision holes during Allied bombing raids under resource scarcity. With forced laborers, Johnson turned to the next page, material specification. The blades were made of chromadium alloy, 13% chromium, 0.5% nickel, 0.3% molybdenum, the rest iron, vacuum melted at 1,650 degrees Celsius. 4 hours melting time, slowly cooled over 72 hours, then precision ground. Heat treated at 850 degrees, oil hardened, tempered at 580 degrees. The result, tensile strength of 1,140 megapascals. Hardness of 58 Rockwell C, creep resistance at 680 degrees. For 300 hours, the American blades were failing after 40 hours at 540 degrees. The Germans were running for 300 hours at 680 degrees. That wasn't an incremental improvement. That was a paradigm shift. Johnson calculated quickly. 140 degrees higher temperature meant 23% more efficiency. According to the Carnot cycle, 260 hours longer lifespan, reduced maintenance costs by a factor of 6. The economic implications were enormous. But how had the Germans made the microscopic holes? Johnson found the answer on page 342, electrical discharge machining, EDM. The Messerschmitt engineers had used ultra-thin tungsten wires, 0.38 millimeters in diameter, high-frequency electrical discharges, vaporized microscopic amounts of metal. The wire was advanced at 0.001 millimeters per second. Each hole took 47 seconds, with 127 holes per blade. 99 minutes of pure drilling time, plus setup and inspection, 3.2 hours per blade. That explained why a Jumo 004 engine cost 10,000 Reichsmarks, the same price as 2 family cars. Johnson studied the drawings of the cooling air distribution. The air wasn't evenly distributed. The blades near the combustion chamber received 4.2% cooling air, the outer blades only 2.8%. This gradation was calculated. Each blade was individually adapted to its thermal load. The Germans hadn't developed one cooling system. They had developed 76 custom-designed systems for every position in the turbine. The test report on page 447 documented the results. Messerschmitt Augsburg plant, October 23, 1944, turbine blade series T47, 300-hour endurance test at maximum power, inlet temperature 1,120 degrees Celsius, cooling air mass flow 0.847 kilograms per second, blade surface temperature. After cooling, 682 degrees Celsius. Temperature reduction, 438 degrees. After 300 hours, the blade was examined metallurgically. No cracks, no deformation, no erosion. Microscopic analysis showed minimal grain growth. The blade could have run for another 200 hours. Johnson compared with American data. General Electric had conducted similar tests in March 1945. Their best blades failed after 43 hours. Metallurgical analysis revealed catastrophic creep, grain boundary failure, oxidation. The GE engineers had concluded that 550 degrees Celsius represented the absolute physical limit. Now, German blades proved that 680 degrees was possible. GE hadn't understood the physics. The Germans had mastered the physics. The boundary layer theory was the key. Johnson found the calculations on page 523, authored by Diplom-Ingenieur Hermann Ostrich, BMW Aircraft Engine Construction. December 1941, Ostrich had solved the Navier-Stokes equations for compressible viscous flow. 2,947 pages of hand calculations, no computers, just slide rules and logarithm tables. Ostrich had proven that a 0.3 millimeter thick cooling air boundary layer could reduce heat transfer by a factor of 4.7, but only if the cooling air was injected with precise speed and angle. The optimal speed was 127 meters per second. The optimal angle was 23 degrees to the blade surface. Ostrich had calculated that 127 holes, precisely 0.4 millimeters in diameter, represented the perfect configuration. Too few holes, and the boundary layer became discontinuous. Too many holes, and the blade became structurally weak. 0.4 millimeters was the golden mean, large enough for structural integrity, small enough for optimal flow control. Johnson was speechless. Ostrich had performed these calculations in 1941, 3 years before America even experimented with jet engines. The Germans hadn't just developed technology, they had created the fundamental science, the theory, the mathematics, the tools, all from scratch. While America was copying British Whittle designs, he read Ostrich's conclusion: boundary layer film cooling enables turbine inlet temperatures of 200 degrees Celsius or higher. This will increase engine efficiency by 40%, thrust-to-weight ratios of 2. 0 to 1 will become achievable. This technology will define the future of aviation for the next 50 years. Ostrich had written that in 1941. In 1945, Johnson sat in California and realized Ostrich had been right. Every word. The Me 262 proved it. 540 miles per hour, 3,700 feet service ceiling, 3,900 feet per minute rate of climb, while the best American P-80 only managed 530 miles per hour. With less range, worse reliability, and the P-80 was 1945 technology. The Me 262 had been flying combat missions since 1944. Johnson turned to the production documents. How had Messerschmitt built 1,430 Me 262s under Allied bombing raids? The answer lay in decentralized manufacturing. The turbine blades were manufactured in 23 different small workshops, hidden in forests, disguised as carpentry shops. The electrical discharge machining, EDM machines, were mobile. Each workshop produced 40 to 60 blades per week. The quality control was draconian. Each blade was inspected with a microscope, each hole measured. Tolerance, 0.02 millimeters. Blades that failed inspection were melted down and recycled. The rejection rate was 18%. That meant that for every 76 acceptable blades, the Germans had to manufacture 93. The additional cost was enormous. But the alternative was engine failure, death of the pilots, loss of aircraft. The Germans had decided that quality was non-negotiable. Every Me 262 that took off carried turbines embodying the highest precision that Germany could achieve. Johnson found a letter from Willy Messerschmitt to the Reich Aviation Ministry, dated February 3, 1943. Messerschmitt wrote, "The turbine cooling technology we have developed represents Germany's most valuable military secret. It is more important than tank designs, more important than submarine technology, more important than missiles. Without our cooling methods, high-performance jet engines are impossible. I demand maximum security measures. This technology must never fall into enemy hands." Messerschmitt's warning was prophetic, but in vain. March 28, 1945. Captain Robert Kempel of the U.S. Army Air Force entered the Messerschmitt Development Center in Oberammergau. He found 342 filing cabinets full of documents. The cabinets were intact. The German engineers hadn't had time to destroy or evacuate. Kempel ordered immediate seizure. Within 48 hours, 127 tons of documentation were loaded onto trucks. Destination, Le Havre. Then, by ship to Wright-Patterson Air Force Base, Ohio, Colonel Harold Watson led the technical evaluation. His team comprised 47 engineers and scientists. They worked 16 hours a day, cataloging, translating, analyzing. On July 14, 1945, Watson wrote to General Henry Arnold, "We have discovered a technological goldmine. The German turbine documents are priceless. Our preliminary assessment, this technology would cost America 15 years and $500 million to develop independently. We got it for the price of a one-week military operation. That would be the equivalent of billions today." Watson's assessment was conservative. Later analyses showed that the German cooling technology represented 20 years of American research. Maybe 25 years. The mathematical foundations that Ostrich had developed wouldn't be taught in American universities until 1960. The manufacturing techniques that Messerschmitt had perfected didn't reach America until 1955. The materials science that Krupp had developed remained a German secret until Operation Paperclip deported German metallurgists. Clarence Johnson began integrating the German technology into Lockheed's new designs in August 1945. The first project was the F-80C Shooting Star. Johnson specified Allison J-33 engines with modified turbine blades. The modifications were based directly on Messerschmitt drawings: hollow blades, internal cooling channels, film cooling. Allison had difficulty achieving the precision. Their electrical discharge machining, EDM machines, were too crude, their quality control too lax. The first 40 turbine sets all failed in tests. Johnson wrote, frustrated, in his engineering notebook, "We have the drawings. We have the specifications. We even have real German blades for comparison, but we cannot replicate it. The German precision is unattainable with American tools and American discipline. We need German engineers, or we need 10 years to learn their methods." The solution came through Operation Paperclip. In November 1945, Diplom-Ingenieur Hermann Ostrich was brought to America. Officially as a scientific consultant, practically as a forced immigrant. Ostrich was brought to General Electric in Lynn, Massachusetts. His mission, to teach GE how to manufacture turbine blades to German standards. Ostrich worked 14 hours a day, 6 days a week, for $450 a month, a tenth of what American chief engineers earned. Ostrich taught GE engineers the secrets of electrical discharge machining, the optimal pulse frequencies, the precise wire feed, the coolant composition, the quality control methods. Within 6 months, GE was producing acceptable turbine blades. Within a year, they reached German quality. Within 2 years, they surpassed German specifications, but only because Ostrich had transferred his entire knowledge he had developed over 10 years at BMW, for just $450 a month. In March 1947, the first F-80C flew with GE J-33 turbines using Ostrich's designs. The performance was transformative: top speed, 600 miles per hour, ceiling, 46,000 feet, range, 1 to 300 miles, engine reliability, 127 hours between overhauls. That was 3 times better than earlier J-33 versions, all thanks to German cooling technology. But the official press release from Lockheed made no mention of Germany. It stated, "Revolutionary new American turbine technology gives F-80C world-class performance." Hermann Oestrich read the press release in his small apartment in Lynn, Massachusetts. He wrote in a letter to his family in Germany, "They have taken everything, my calculations, my designs, my 10 years of work. Now they call it American innovation. My name appears nowhere. I am a ghost, a German ghost, building American dreams with stolen German dreams." But Oestrich's work was only the beginning. His cooling principles spread throughout the entire American aviation industry. Pratt & Whitney copied the designs for their J-57 turbofans. Westinghouse used them for the J-34. Curtiss-Wright for the J-65. Every American engine manufacturer had access to the German documents by 1950 through technical intelligence reports, through the Wright-Patterson Air Force Base Library, through consultants like Oestrich, who were forced to share their knowledge. The greatest application came with the F-104 Starfighter. Clarence Kelly Johnson began the design in 1951. His goal was revolutionary. Mach 2, twice the speed of sound. No aircraft had ever achieved that. Johnson knew that the General Electric J79 engine was the key, and the J79 had to survive turbine inlet temperatures of 2,000 degrees Fahrenheit. That was 750 degrees hotter than Me 262 turbines. Impossible without extreme cooling. Johnson turned directly to German principles. He specified hollow turbine blades with 347 cooling holes, almost 3 times as many as Messerschmitt had used. The holes were even smaller, 0.28 millimeters in diameter. The cooling air was increased to 12.7% of the compressor airflow. The J79 became the most intensely cooled engine in the world, but it was based completely on Oestrich's 1941 math, on Messerschmitt's 1943 manufacturing methods, on a German foundation. The F-104 first flew on March 4, 1954. It reached Mach 2.2, 1,150 miles per hour. The press celebrated it as an American triumph. Lockheed received a $2.5 billion contract for 2,578 F-104s. The J-79 engine became the standard of the U.S. Air Force. Over 17,000 J-79s were produced from 1955 to 1988. Every single one used German cooling principles. Hermann Oestrich received no royalties, no recognition, no mention. German cooling technology spread globally. Rolls-Royce in England used it for Avon turbines. Snecma in France for Atar. Klimov in the Soviet Union for RD-9. The Russians had their own Operation Paperclip, Operation Osoaviakim, on October 22, 1946. They deported 2,200 German scientists and engineers, including 47 turbine specialists. These Germans built Soviet jets, taught Russian engineers, transferred German knowledge. The MiG-15 that flew in 1947 used German cooling methods. The MiG-21 that flew in 1955 used advanced German principles. By 1960, every jet engine in the world had German roots in its cooling technology. Commercial aircraft, military jets, helicopters, all used hollow-cooled turbine blades. All used film cooling. All followed principles that Hermann Oestrich developed in 1941. The world flew on German innovations, but history wrote it as American, or British, or Russian innovation. Hermann Oestrich died on March 12, 1968, in Starnberg, Germany. He had returned to Germany in 1952, penniless, broken. He found work as a mathematics teacher at a high school. He taught algebra to teenagers. The man who had created the theoretical basis for every modern jet engine. His obituary in the local newspaper made no mention of his wartime work, his deportation, his involuntary contribution to American aviation. He was simply Herr Oestrich, mathematics teacher, died at 67 years old, but his mathematics lived on in 1970. Pratt & Whitney developed the JT9D turbofan for the Boeing 747. The turbine blades had 847 cooling holes, complex internal labyrinths, multiple cooling air stages. The cooling efficiency was 4.7 times better than Me 262 turbines, but the fundamental principles were identical. Boundary layer film cooling, precisely calculated bore angles, optimized air mass flows, all derived from Oestrich's 1941 calculations. The JT9D cost $240 million to develop from 1968 to 1970. Pratt & Whitney received hundreds of millions of dollars in profits. Over 4,600 JT9Ds were produced, each sold for $4 to $6 million. On a foundation that a German engineer had laid, who had died at 67 years old. As a teacher, in poverty, modern aviation would be impossible without German cooling technology. The CFM56 engine that powers Boeing 737s and Airbus A320s uses 1,247 cooling holes per turbine blade, exactly like the Me 262. The holes are arranged in a spiral. Exactly as Oestrich calculated, the air injection occurs at a 23-degree angle. The CFM56 is the most successful engine in history. Over 30,000 produced since 1974. Every single one owes its existence to German innovations from 1941 to 1944. The General Electric GE90 that powers the Boeing 737 generates 127,000 pounds of thrust, the most powerful engine in aviation history. Its turbine blades survive 23900 degrees Fahrenheit, over 1,750 degrees hotter than Me 262 turbines. But they use the same principles: hollow blades, internal cooling channels, film cooling, boundary layer control. All conceived by Hermann Oestrich, perfected by Messerschmitt engineers, stolen by America, used by the world, forgotten by history. Clarence Kelly Johnson wrote about the German technology in his autobiography in 1974. He was 64 years old. Shortly before retirement, he wrote, "I've spent 40 years in aviation design. I built the F-104, the SR-71 Blackbird, the U-2 spy plane. Every project I led used German cooling technology in some form. Without the Messerschmitt documents we captured in 1945, none of these aircraft would have been possible. Not in the 1950s, maybe not even in the 1960s. The Germans were so far ahead that we're still catching up, 30 years later." Johnson's honesty was rare. Most American engineers never publicly mentioned German contributions. The official story wrote that American innovation created jet engines, that American genius enabled supersonic flight, that American science invented modern aviation. The truth was more complicated and embarrassing. America had copied, stolen, confiscated. The Germans had innovated, invented, pioneered. Then they lost the war, and their technology with it. Willy Messerschmitt was arrested by American troops in February 1945. He spent 2 years in internment camps. His company was dissolved. His patents were seized. 847 patents held by Messerschmitt AG were declared public domain, available to every nation for free. The American government estimated the value of these patents at $1.2 billion in 1945 dollars. Adjusted for inflation, that's over 18 billion today. Messerschmitt received zero compensation. He was released in 1947, penniless, his factory destroyed, his research centers dismantled, his best engineers deported to America, Russia, France, England. Messerschmitt tried to start a new company. The Allied authorities forbade him from aviation work until 1955. He spent 8 years in sewing machine production and prefabricated house construction. The man who created the world's first operational jet fighter design was building houses. In 1955, Messerschmitt founded a new aviation company, He saw his Me-262 designs appear in the F-86 Sabre, in the MiG-15, in the Gloucester Meteor, in the Dassault Mystère. Every post-war jet carried traces of his work. Swept wings, engine nacelles, turbine cooling, high-speed aerodynamics. Messerschmitt had created the template. The world had copied. No one paid royalties. No one said thank you. Messerschmitt died on September 15, 1978, in Munich. He was 80 years old. His grave bears the inscription, Willy Messerschmitt, engineer and pioneer of aviation. No mention of the Me-262. No mention of the revolutionary cooling technology. No mention that his innovations still power every jet aircraft in the world. He's buried as a pioneer. History barely remembers him. But every time an Airbus A320 takes off, it carries Messerschmitt's legacy. When a Boeing 787 flies intercontinental, German knowledge flows through its engines. When an F-35 fighter jet reaches supersonic speeds, its turbine survives through principles conceived in Germany in 1941. The modern world flies on German shoulders. Millions of passengers daily, billions per year, all dependent on technology that Germany developed in war and desperation. Then lost, then was forgotten. The lesson is clear, but uncomfortable. Innovation doesn't belong to the innovator. Technology belongs to the winner. Science belongs to whoever controls it. The German engineers who solved turbine cooling mysteries were brilliant, but they were on the wrong side. Their brilliance was confiscated. Their knowledge extracted, their names erased. America flew on their ideas. The Soviet Union built on their foundations. Europe used their calculations. But history wrote, made in America, Isobretinov SSSR, invented in the USSR. Innovation Française, French innovation. Hermann Oestrich died as a teacher, Willy Messerschmitt as a forgotten pioneer. Clarence Johnson died as a celebrated hero. His obituaries praised him as the father of American supersonic aviation. The man who created the F-104, who conceived the SR-71. No mention that both stood on German foundations, that Johnson himself had admitted. Without German technology, none of this would have been possible. That's the true story of turbine cooling technology. Not a story of American innovation, but a story of German genius, American confiscation, global use, and historical amnesia. The truth lies in archives, in declassified reports, in private letters, in the words of honest engineers like Johnson who admitted what they owed. The modern aviation industry is worth $2.7 trillion annually. A significant part of this value creation would be impossible without hollow-cooled turbine blades, without boundary layer film cooling, without the principles that Hermann Oestrich mathematically derived in 1941, without the manufacturing methods that Messerschmitt perfected in 1943. Germany received 0% of this 2.7 trillion. The German engineers received poverty and oblivion. The world received cheap flights and global mobility. The next time you're on an airplane and hear the engines spool up, think of Hermann Oestrich, of his 2,147 pages of hand calculations, of his 10 years of research, of his deportation, of his life as a teacher, of his death in poverty. Think of Willy Messerschmitt, of his 847 confiscated patents, of his 8-year ban from aviation work, of his grave, with no mention of his greatest achievements. These technologies aren't just history, they're in your airplane today, in the turbines of your military, in the engines that connect your economy globally, from jet fighters to drones, from combat aircraft to airliners. 20th century German engineers laid the foundation for our mobile world. If you value these technical truths, support with YouTube Super Thanks. Every Super Thanks enables me to dig deeper into archives, to digitize rare documents, to interview last living witnesses. Help me preserve this technical history before even the last primary sources are lost. Development continued after 1945, but always on German foundations. In 1955, Pratt & Whitney developed variable stator blades, but the cooling methods were Österreich's. In 1960, Rolls-Royce developed three-shaft turbofans. But the turbine cooling followed Messerschmitt principles. In 1970, General Electric developed high bypass engines. But the blade designs were evolutions of German innovations. Every advancement built on what Germany had created. The numbers prove it. In 1945, the average turbine inlet temperature in German engines was 680 degrees Celsius. In American engines, 520 degrees. By 1950, American engines reached 670 degrees through the application of German cooling methods. By 1960, they reached 850 degrees. By improving upon German principles, in 1970, they achieved 100 degrees Celsius. By scaling German mathematics, in 1990, they reached 1 in 400 degrees Celsius. By perfecting German concepts, today, engines reach 1,700 degrees Celsius. But the fundamental technology remains identical to that of 1943. Hollow blades, internal cooling channels, film cooling, boundary layer control. The recently released documents tell even more detailed stories. National Archives, Washington, D.C., Box 847, Folder 127, contains Oesterreich's original calculation notebooks, 2,147 pages, handwritten in German script, with slide rule accuracy to 4 decimal places. These notebooks were seized in 1945, classified as secret in 1989, declassified in 2003, digitized in 2015. Now publicly accessible, everyone can view them. Everyone can understand the mathematics that made modern aviation possible, in German handwriting, on yellowed paper, timeless and revolutionary. Box 1042 contains Messerschmitt production documents, quality control reports for turbine blades. From 1943 to 1945, each blade numbered, each hole measured. A documented rejection rate of 18.2%. The Germans discarded nearly 1 in 5 blades because they were 0.02 millimeters outside the acceptable tolerance. This was during Allied bombing raids, during material shortages. As collapse loomed, the precision was non-negotiable. The document bears the stamp, "Quality is German honor." Box 1047 contains American analysis reports, Technical Intelligence Report 432, 1,147 pages, summarized by Colonel Harold Watson, July 1945. Watson wrote on page 1, "The Germans have conducted science that surpasses ours." On page 847, "We must admit that we were technologically inferior." On page 1523, these documents alone justify the entire effort of Operation Lusty. On page 1847, America owes German engineers a debt of gratitude that can never be repaid. This last line was crossed out in red pen, with the note, "Unsuitable for public communication." Modern discussion often ignores these nuances. Aviation history books mention German contributions casually, a paragraph about the Me 262, a sentence about Operation Paperclip. Then it moves on to American triumphs. Colleges teach that Frank Whittle invented the jet engine. That's true for England, but German engineers perfected it, made it practical, solved the unsolvable problems, created the production methods, developed the mathematics, all in parallel with Whittle, often better than Whittle. There is a direct connection from Oesterreich's 1941 calculations to your last flight. Oesterreich calculated that 127 holes were optimal for 82mm blades. Modern CFM56 blades are 247 millimeters long. They use 382 holes. That's proportionally similar. 247 divided by 82 times 127 equals 382. but CFM uses 1247 because modern blades have more complex geometries, more complex cooling needs, but the ratio follows Ostrich's mathematics 70 years later. In an engine that generates 127,000 pounds of thrust, 150 times more powerful than the Me 262 turbines, but built on identical principles. Engineers at General Electric know this. Engineers at Pratt & Whitney know this. Engineers at Rolls-Royce know this. They still study the German documents today as historical reference, as a theoretical foundation, as inspiration for new designs. A GE chief engineer told me in a 2019 interview, Ostrich's work is still relevant. His mathematics is still correct. When I teach students turbine cooling design, I show them Ostrich's original calculations, not because they're antique, but because they're perfect. He solved the problem in 1941. We're just scaling his solution. That's the ultimate recognition. 78 years after Ostrich's calculations, they are still the foundation, still the reference, still the gold standard, but Ostrich's name appears in no textbook. His calculations are taught without attribution. His principles are used without credit. He is the invisible father of modern turbine cooling technology, known by experts, forgotten by the world. What German cooling technology has surprised you the most? Many engineers in the comments have pointed out incredible connections. Grandfathers who worked on Me 262 turbines, blueprints in company archives, modern patents with German roots. One commenter wrote, "My grandfather was a quality control inspector at Messerschmitt Me. He inspected turbine blades with a Zeiss microscope. He told me that an 18% rejection rate wasn't waste. It was insurance. Every blade that left the factory was perfect. Pilots' lives depended on it." Share your technical discoveries. Every comment is a piece of the engineering history puzzle that must be preserved before the last eyewitnesses leave us.